Good afternoon, students. So we'll continue the problems on stiffness matrix method of analysis. We'll do problems with stiffness matrix size of 3 by 3 today. I'm going to share the screen now. Hope all of you can see the screen. So today we are going to discuss few more problems on beams. So can you see this problem? Analyze the continuous beam shown in the below figure by displacement method. Take EI value as constant. So you can see here span A to B there is overhang portion, B to C there is a point load of 80 kilonewton which is acting at the center, and from C to D you have a point load of 80 kilonewton which is not at the center. It is placed at a distance of 3 meter from support, 4 meter from support C and 2 meter from support D. So overhang portion, it will come as a moment at support B. That will be the final moment. So that will be in the anti-clockwise direction. How much it is? 80 kilonewton meter. So you can see here 40 into 2. So it will act as a moment of 80 kilonewton meter in the anti-clockwise direction. So here overhanging beam portion load is considered as a final moment acting at support A. So you can see here acting at support A, it is in the anti-clockwise direction 80 kilonewton meter. So now here there is a mistake. Here it should be B, C and D. So how many unknowns are there? So hinge, it will prevent horizontal and vertical translation. Since it is a beam, I'll neglect axial deformation. So even support C, it will prevent the vertical translation, and support D will also prevent vertical translation. Since I have assumed this axial deformation is 0, so we can notice that there are 3 degrees of freedom. At support B, it will allow rotation, support C also allow rotation, and support D also allow rotation. So the unknown displacements, that is degree of freedom, is equal to 3. Which are those 3? Theta B, theta C and theta D. Now, what is the next step? You have to assign the coordinates for these 3 degrees of freedom. Hence, the coordinates selected are as shown below, right? So, here, now this overhanging portion, instead of overhanging portion, you have we can see that there is a anti-clockwise moment of 80 kilonewton meter A to C and C to D span, right? So, now I'm assuming that at coordinate B, let the rotation be in the clockwise direction. At C also clockwise direction, and at D also clockwise direction. So coordinate 1, coordinate 2 and coordinate 3 all are in clockwise direction. So next, what is that we need to calculate? We need to restrain the structure. We have to restrain the structure. So I have put a fixed support at B, C and D. So that is the second step, right? After finding out the degree of freedom and after assigning the coordinates, next we have to restrain the structure. So I have restrained the structure at B, C and D. Now what is that next I have to do? I have to calculate the fixed end moment. So and also here final force vector I have calculated in the beginning itself. So P is equal to, at support B you have a moment of external moment of 80 kilonewton. The assumed direction was, here assumed coordinate was in the clockwise direction, but this external moment which is coming at support B is in the anti-clockwise direction, hence it is minus 80. Do we have any other moment at support C or support D external moment? No, there is no external moment at support C or support D, hence it is 0, 0. Right. So next, what is that next we have to do? Next, I have to calculate fixed end moment at support, fixed end moment due to this point load. How much is the point load? How much is the point load? It is 60 kilonewton. So MFBC is equal to minus WL by 8. As it is minus sign, it indicates that it is in the anti-clockwise direction. You can see here it is in the anti-clockwise direction. There are minus WL by 8, so it is minus 60 kilonewton meter. Next MFCB, it is plus WL by 8, so it is plus 60 kilonewton meter. Next for MFCD, again it is anti-clockwise, so MFCD is equal to minus WAB square by L square, and MFDC is equal to plus WBA square by L square. WAB square by L square, it will come around minus 35.5 kilonewton meter, and MFDC is equal to plus WBA square by L square. How much you are going to get? You are going to get 71.11 kilonewton meter. Then what is that next you have to do? You have to calculate the forces in the restraint structure, where we had applied the coordinate at support B, support C and support D. Support B, you have only span BC. What is MFBC value you have got? We have got how much it is? Minus 60. So I have written minus 60 here. At coordinate 2, that is at support C, it is connected to span CB as well as CD. So MFCB and MFCD. What is MFCB? MFCB is plus 60. MFCD is minus 35.5. So plus 60 minus 35.5, if I do, what is the answer? It is 24.45 kilonewton meter. Then what is MFDC? MFDC is it is in the clockwise direction, so plus 71.11 kilonewton meter. So it is plus 71.11 kilonewton meter. Okay, so once you know the forces in a restraint structure, what is next you have to do? You have to calculate the stiffness matrix. Okay, first let me apply a rotation of 1 at support B, and I'll restrain the moment, at support C and at support D it is 0. Only theta B is equal to 1, theta C and theta D is equal to 0. So what is that when you are applying a moment in a clockwise direction like this, so there will be a sinking here. Okay, so now it is its effect will be only on the span BC. Okay, so it is not, its effect will not be there for span CD, right? So what is K11? What is the force developed at coordinate 1 due to rotation, a rotation of 1 at coordinate 1? So it is, what is the answer? 2EI by L into 2 theta B plus theta C minus 3 delta by L. Anyway, theta C is 0 because it is a, there theta C is equal to 0, theta D is equal to 0. Only theta B is equal to 1. So 2EI by L into 2 theta B plus theta C minus 3 delta by L1. So there is no translation, that is 0. Theta C is also 0. Only theta B is equal to 1. And EI value is how much? 2I. So 2E in place of I value, again you are going to put 2I. So 4EI 4E into 2I by 8, if you do, what is the answer? You are going to get EI. Then K21, what is the force developed at coordinate 2 due to, what is the force developed at coordinate 2 due to unit rotation at 1. So that is, again it is connected to span CB, right? So what will happen? 2EI by L into 2 theta B plus 2 theta C plus theta B minus 3 delta by L. Anyway, 2 theta C is 0. Theta B is equal to 1. If you do, what is that you are going to get? EI, in place of EI you are going to write 2I. So it is 2 2s are 4. 4 EI by length is 8 meters. So it will come 0.5 EI. Next, what is the force developed at coordinate 3 due to rotation at coordinate 1? So coordinate 3, at coordinate 3 there is no effect due to this displacement at coordinate 1. Hence it is K31 is equal to 0. Okay. Next, what happens when there is a unit displacement at coordinate C, at coordinate 2, okay, or at support C? So what happens when you apply a clockwise moment here? This will undergo hogging and this will undergo sagging as shown in the figure. So when there is a displacement at coordinate 2, what is its effect at coordinate 1, at coordinate 2 as well as at coordinate 3. For that we are going to develop a matrix. So K12, what is K12? K12 is what is the force developed at coordinate 1 due to rotation at coordinate 2. So it is, you are going to write 2 EI by L into 2 theta B plus theta C minus 3 delta by L. 2 theta B and theta D is equal to 0. Only rotation is allowed at support C, right? So only theta C is left. So 2E into I value is 2I divided by 8. If you do, what is that? You are going to get 0.5 EI. Then what is K22? What is the displacement force at coordinate 2 due to unit rotation at coordinate 2? So again it is 2 EI by L into 2 theta C plus theta B minus 3 delta by L. Theta B anyway it is 0. When so it will be 2 into 2 into 2, so it is 8 16 EI by 8. Then and this side it is I value is 1.5, so it will be 2 theta C 2 EI by L into 2 theta C plus theta D minus 3 delta by L. There is no horizontal or vertical translation, so delta will be 0. Then theta D is also 0, only theta C will be there, so it is 2 theta C. In place of theta C, write 1. When you calculate that, you are going to get 2E into 1.5 EI by 6, so it is 2 EI. Then K32, what is the force at coordinate 3 due to unit rotation at coordinate 2? So what will happen? 2 EI by L into 2 theta D plus theta C minus 3 delta by L. Theta D anyway it is 0. In place of theta C if you write 1, what is the answer you are going to get? And I value is 1.5. So you are going to get 0.5 EI. Similarly, you have to do for unit displacement at D. That is when you apply a unit rotation at coordinate 3, what is its effect at coordinate 1 and coordinate 2? Right. So what will happen when there is a rotation here in the clockwise direction? It will undergo hogging. There is no effect on span BA. Right. So K13 is equal to 0. What is K23? That is force developed at coordinate 2 due to unit displacement or unit rotation at coordinate 3. So it is again 2 EI by L into 2 theta C plus theta D minus 3 delta by L. Theta C anyway it is 0. Theta D, in place of theta D write 1 and in place of I write 1.5 I. So you are going to get 0.5 EI. Then again K33. What is K33? What is a unit, force developed at coordinate 3 due to displacement at unit displacement or unit rotation at coordinate 3. So that is again 2 EI by L into 2 theta D plus theta C minus 3 delta by L. 3 delta anyway 0, theta C is 0. In place of 2 theta D, 2 into 1. So if you do, it is 4E into, in place of I, if you put 1.5 I divided by 6, you are going to get EI. So next write down the stiffness matrix in the column wise, that is K11, K21, K31, K12, K22, K32, K13, K23 and K33. If you write, what is that you are going to get? 1.50, 0.52, 0.5, 0.51, delta 1, delta 2, delta 3. And P value, we have already calculated the final forces minus 80, 0, 0. And PL value, you had got minus 60, minus of minus plus 60, plus 24.45, minus into plus minus 24.45 and plus 71. So here minus side. So minus into plus minus 71.11. So when you calculate displacement, this is what you are going to get. Theta B is equal to minus 27.035 by EI. Theta C is equal to 14.07 and theta D is equal to minus 78.145 by EI. Okay, so when you apply the slope deflection equation here, MAB is equal to MFAB plus 2 EI by L into 2 theta A plus theta B minus 3 delta by L. 3 delta is 0, theta A is also 0. So whatever answer you are going to get, when you apply the equation and solve it, you are going to get minus 80 kilonewton meter. Similarly, calculate MBC, MCB, MCD and MDC. MDC obviously you should get 0 because D support is, what type of support was D in the problem? It was a hinge. It was a roller support and it was a last support. So obviously moment has to be 0. Right, at MAB also it is, how this minus 80 kilonewton meter came, it was a overhanging beam load, right? So here no need to apply the slope deflection equation. For overhang portion, no, you cannot apply the slope deflection equation, that you have already got how much it is, minus 80 kilonewton meter, right? So then MBC you have to apply, MCB, MCD you have to apply the slope deflection equation. For MTC, if you apply also equation, you are going to get 0 since it is a last support and it is a roller support. Okay. So what we discussed today, we discussed a problem with the stiffness matrix size of 3 by 3. So same problem I want you to do, but instead of taking overhanging load at support A at point A as 80 kilonewton, take 40 kilonewton and all other loads, beam, span, dimensions, everything remains same. So identify the degrees of freedom, determine the stiffness matrix, determine the unknown displacements and calculate the final moments. Okay. So in the next class we'll discuss sinking support problem. How to analyze a beam using stiffness matrix when there is a sinking in the support. Thank you.